we're going to have a look at bonding. We're going to look at all the different types of bonding. We're going to cover the GCSE material. We're going to look at giant bonding, intermolecular bonding, intramolecular bonding, and so on. Okay? This is a topic that pupils typically find hard because it links together different parts of the syllabus. Okay, but basically, this is quite straightforward once you get your head around it. Okay. Right. So, chemical and physical bonding, ionic bonding, covalent bonding, simple molecules, van der Waals forces, electronegativity, hydrogen bonding, coordinate bonding, molecular solid, covalent networks, and metallic bonding. Everything that you need to know about bonding. So, if we could be quiet in the back, please. Right. Very importantly, okay, the physical properties are determined by the type of bonding present. Okay? If you get a question that's got any mention of temperature, okay, when it comes to boiling point, it's going to have something to do with bonding. Okay, the type of structure present. So, noble gases, first of all, are all relatively or totally inert. Okay? And that's because of their electronic structure. They've got a full outer shell, they don't need to gain or lose electrons to have a full outer shell, therefore they don't bond. Okay? Atoms without the electronic structure of a noble gas will form bonds to have the noble gas configuration, i.e. a full outer shell. There are various ways they can do that, and the way they do that depends on the atom's position in the periodic table. So, I don't really draw this distinction between chemical and physical bonds. What we have, though, are these 7 types of bonding. Okay, and these are, there's a very specific order to them. Covalent bonding, and then dative covalent bonding, okay, very, very strong indeed. Okay, typically after that you've got ionic, followed by metallic. The 3 types of intermolecular bond, or force, are hydrogen bonds, then dipole-dipole, and then van der Waals. If you are going to melt something, you are going to have to break one of these bonds. Okay? And the boiling point, the melting point, is dependent on which of the bonds you have to break and their relative strength. So let's start with ionic bonding. This is basically where you have something like sodium, which has got an electron configuration of 281, or in A-level terms, 1s2, 2s2, 2p6, 3s1, and it gives this outer electron to chlorine, which is electron deficient, okay? And in doing so, they both end up with a full outer shell. So sodium here, sodium plus has now got a full outer shell. Chlorine is now the chloride ion, it's got a full outer shell. There's been a transfer of electrons. This is now positive, that is now negative, and those two will attract each other. And this goes right back to GCSE, but you've really got to understand it. Okay, so electron transfer. We're not going to worry too much about the formation of ions, other than if you start with Mg and you go to Mg+, that has now not got a full outer shell. So magnesium in ionic compounds is going to be Mg2+, it's going to lose both the outer electrons. The chlorine is going to gain an electron, the oxygen is going to gain 2 electrons. Okay? So the formula of magnesium oxide is MgO, because it's Mg2+ and O2-, whereas the formula of sodium oxide is Na2O. You need 2 sodiums to give away 1 electron each to react with an oxygen that needs to gain 2 electrons. So for the oxygen to gain 2 electrons, it has to react with 2 sodiums. So Na2O, MgO, and MgCl2. Because you need 2 chlorines to each receive an electron, okay, for the magnesium to go to Mg2+. Does that make sense? Okay, so that's sort of top-end GCSE. Oh, we've got some little animations. So here we have, an electron, and it's gone off on a little journey to the chlorine atom. Isn't that sweet? And we then get the sodium ion and the chloride ion, and an electron's transferred, and I don't think I really need to say this anymore, so here's Mg, there goes 1 electron. There goes the other electron. Mg is now Mg2 plus, the chlorine is Cl minus, and there's Cl minus. Are we happy with that? Therefore, MgCl2. And what you end up with is an ionic structure like this of alternating positive and negative ions. You don't need to worry about the exact structure. You should be able to draw, you don't need to come out with anything as complicated as this, you should be able to draw at least 4 atoms, okay, preferably 8. If you can draw 8, okay, that's like 4, so positive, negative, and then behind it, negative, positive, okay, or in some order to show alternating pattern. If you can draw 8, we're all good. This one here is actually face-centered cubic structure. So this is one face there, and you've got an opposing ion in the centre of it, but you don't need to worry too much about this. And there's the other one, so each one has got 6 nearest neighbours, okay, face-centered cubic. Ionic compounds, high melting point. Why? Strong attraction between the ions. Brittle. Why? Because the moment you give them enough energy, the layers just shatter away from each other. Okay? There's no flexibility. You hit an ionic substance, it breaks. They don't conduct when solid. No free electrons to move around. And the positive and negative ions can't move. The moment you dissolve them in water, or alternatively melt them, the ions are free to move. You can apply voltage to it, the ions move around, and the ionic substance conducts. They do dissolve in water, okay? They don't dissolve in non-polar solvents such as petrol. So salt dissolves in water, but not petrol. Water is a polar solvent, will dissolve anything that's polar. Petrol is a non-polar solvent, will dissolve most things that water doesn't. Okay? There are not that many substances that don't dissolve in one or the other of them. Okay? To some extent. So, brittle ionic lattices. The moment you manage to shift one lot of atoms, relative to the other lot, it's going to repel and the whole thing's going to fall apart. So, solid ionic compounds do not conduct electricity. We've done this, molten ones do. And let's move on to covalent bonding. Okay? The previous statement I said about water and petrol, between them they dissolve a lot of things. There are, of course, some things that don't dissolve in either, such as petrol cans. Okay? You don't want something that does. The petrol can, it's got to make sure that it doesn't react to the petrol, and also if you leave it out in the rain, it's got to make sure you don't dissolve it there. Okay, but a lot of substances, such as most plastics, okay, will dissolve in a non-polar solvent, such as petrol or chemically hexane, something like that. So, covalent bonding, you know this, okay? A covalent bond is a pair of shared electrons. Yeah? It's where a pair of electrons is shared between 2 atoms. And what you have here is a positive nucleus attracted to the negative electrons, and so on. So you get it between atoms of the same elements, you get it between atoms of different elements on the right-hand side of the table, you get it when one of the elements is in the middle of the table, and with head of the group elements, okay, period 2. Basically, whenever you have a small difference in electronegativity, you get covalent bonding. Okay? When one of them really can't pull the electrons away from the other, you get covalent bonding. Okay? So here, no difference in electronegativity, covalent bond. Here, little difference in electronegativity, covalent bond. Here, again, not that much difference, okay? A bit, okay, but not lots and lots. And here, Be is metal, okay, but because it's a top row metal, it actually has quite a high electronegativity, and thus there is covalent bonding occurring. Sometimes you don't get the full outer shell. Al and AlCl3 ends up with 6 electrons in its outer shell, and it can receive a pair of electrons from a dative covalent bond very readily. Others stop after doing some covalent bonding. Ammonia has got 3 bonds, okay, but it's got a lone pair of electrons. And so on. What you can also get is elements in the 3rd period exceeding 8 electrons. PCl5, the phosphorus, has got 5 pairs of electrons in its outer shell. That's 10 electrons. And to do that, it has to actually stick some in its d orbital. Okay? This is why we actually say that phosphorus has got 3d orbital. It just doesn't fill it. Okay, you know there's that confusion of why does it go 4s 3d? Yeah? This is why. Because the ones with the 3p shells have got unfilled 3d shells. Okay? Moving on. Basically, you have here an s orbital, and here you have another s orbital, and the two s orbitals overlap and contain a pair of electrons. Hydrogen, therefore, will join together. Oh, a little bit of animation going on, and there we go. Will you look at that?
Oh, I missed it.
Tough.
Actually, it's distracting.
And ways to represent the molecule. Okay, I would normally represent that as a dot and a cross to show one from each side, like that, no problem. If you look at hydrogen chloride, there's chlorine, there's hydrogen, and the two, oh wow, that is amazing, that is, there you go, covalent bond. And here you have standard cross and dot notation. Methane, off it goes. So this is why you've got a ridiculous number of pages in your handout, isn't it? There we have it. And different ways of representing the molecule. Ammonia, water, yawn, yawn, yawn. Oxygen, two pairs of electrons. Okay, double bond. So, they're bonding. Well, they're joined together by covalent bonds, and you know covalent bonds are really strong, so obviously they've got a really high melting point. Which makes the important point that actually they don't. They have a very low melting point, and that is because you don't break the covalent bonds. That's the mistake pupils make. You don't break the covalent bonds. When you boil water, you still have discrete H2O molecules. So now we have to think about what is it that holds the H2O molecule to the neighbouring H2O molecule. And that is where you get intermolecular forces. So let's move on to van der Waals forces. Basically, at any one point, you don't get even distribution of electrons. Okay? In this case, you've got slightly more electrons over here than you have over there, so that side becomes slightly negative, that side becomes slightly positive, and these temporary dipoles can line up, and that is what a van der Waals force is. Okay? And what will actually happen is this delta minus here will induce a delta positive there, okay? And then it will all flick back and so on. So, you get this where you have no other form of bonding. Oh, sorry, you get this with every molecule, okay? Every molecule you get this. So, even if you've got nothing else, you've definitely got van der Waals forces. However, if you have one atom that's more electronegative than the other, then what you get is a polar bond. Okay? So different atoms have different electronegativities. The polar bond is where one end you've got a more electronegative element, it's slightly minus, the other end therefore becomes slightly plus. Yep. Therefore you've got a polar bond. And what happens is the polar bonds, we're not going to worry too much about that, the polar bonds line up. Okay, so your delta positive, your delta negative, these line up, okay, and you've got dipole-dipole attraction. Now, when you have dipole-dipole attraction, you also have van der Waals forces, and the van der Waals forces in total are stronger. It's that the dipole-dipole attraction is a little bit extra on top of the van der Waals forces. Does that make sense? Okay, it's like a little bit extra on top of. So, polar molecules, hydrogen chloride, tetrachloromethane, and water. Except tetrachloromethane is non-polar. And the reason it's non-polar is, although each bond is polar, overall the molecule isn't. There's no line that you can draw through that molecule where one side becomes negative and one side becomes positive. Does that make sense? So it's not a polar molecule. Whereas water, below my lightsaber, slightly positive, above it, slightly negative. Yeah, so that is a polar molecule. It's very important this. Polar bonding doesn't always lead to a polar molecule. There has to be one side positive, one side negative. Does that make sense? So, polar, non-polar, polar again.
Oh my god. Wow. Oh my god. What the heck?
So here we have the water stream being deflected very slightly, and that proves that water is a polar molecule. Okay. What we now need to move on to is the boiling points of the hydrides. And if we look at, say, CH4SO H4, GH4, SNH4, there is a very clear trend in the boiling point. As the molecules get bigger, they have more electrons, therefore strong van der Waals forces. And as you can see, there is quite clearly not the same pattern with group 5. Okay, with group 5, you've got a nice clear pattern there, but ammonia messes it up. And it's the same with group 6, and it's the same with group 7. And what that tells us is that with NH3, H2O and HF, something else is going on. Altogether, what else is going on? Hydrogen bonding. Okay? So here's my graph for the group 4 hydrides. There it is for group 5 hydrides, and there it is for group 6 hydrides. And it clearly shows that these two here are out of whack, and there's the HF. Okay? These three all have hydrogen bonding. For hydrogen bonding to take place, you need oxygen, nitrogen or fluorine attached to a hydrogen and a lone pair. Okay? So, it's basically an extension of dipole-dipole interaction, okay? But it's to do with the fact that these three, F, N and O, are very small. Okay? And here is a representation of hydrogen bonding in water. And as you can see, the hydrogen is bonded to the lone pair on a neighbouring oxygen. Hydrogen bond is, in this case, represented by 4 dashes, though I think by convention is represented by 3 dots. And they have a picture of it in ice. This is the reason that ice, okay, has got such a high melting point, okay, relative to other things that are similar sizes on, because it forms 4 hydrogen bonds per molecule. 1 hydrogen bond from the lone pair that way, 1 hydrogen bond from the lone pair that way, 1 hydrogen bond from the hydrogen that way, and the other hydrogen bond from the hydrogen that way. Now, ice has got a very unusual property compared to water in as much as it's less dense. And the reason it's less dense is it gets locked into a structure where it's forced into this tetrahedral structure. Okay? And in doing so, there are then gaps in the structure. There is more space, okay, inside the structure of ice than there is in the structure of water. Because if the molecules are free to flow into the space, then it's slightly more dense. Does that make sense? Sorry? No, that's slightly different. It's not to do with the fact that it's got more of a vacuum in it. But basically, when ice freezes, or when water freezes and turns into ice, the structure gets locked. And it has slightly more space in it than in liquid water, and as a result of more space in it, it expands, becomes less dense. Okay? Hydrogen bonding in HF, as you'd expect, H, hydrogen bond F. Dative covalent bonding, lone pair, can be donated to something else, okay, and you have covalent bond where both electrons have come from one side. That's all a dative covalent bond is. Here's a more complicated example. We have NH3 and BF3, and you end up with that bit there. Molecular solids. So here we have iodine. I don't know how that's going to show up on camera. Lots and lots of I2s, okay, and they're all single bonded to each other, but they then line up, okay, and iodine is held together by van der Waals forces between the molecules. So you don't break the covalent bond, you break the van der Waals force, okay? Giant structures or macromolecular structures, they have very high melting points. And that is because you've got a large structure. Okay? It could be covalent, ionic or metallic, but a large structure where every atom is strongly bonded to another one. Okay? So a pure single diamond would be one exceptionally large molecule. Okay? So you actually have to break the covalent bonds to break diamond. They have a very high melting point, they don't conduct electricity because they don't have mobile electrons or ions, apart from metals obviously, and they are very strong. Okay? So diamond has got this structure, every carbon covalently bonded to 4 others. High melting point, very strong, doesn't conduct. Graphite. Layers of very strongly bonded atoms, but the attraction between those layers is very weak. Okay? So the layers can slide over each other, okay? Which means that a pencil can work. You rub in this layer of atom, you put your pencil down, draw it across, that layer of atoms stays put, next layer of atoms move over, when that next layer of atoms is then next to the paper, that one stays put, and so on. So theoretically, okay, a pencil leaves behind a single molecular layer of graphite. Okay? In practice it doesn't happen like that, but in theory it could. So here we have the macromolecular structure of diamond and the structure of graphite. You then get something like silica, okay, which has got the same structure as diamond, with silicon atoms with oxygen in between. Again, very high melting point, silicon dioxide. Which brings us on to metallic bonding. So you should be familiar with this idea of positive ions and delocalized electrons from GCSE. The stronger the attraction between the positive ions and delocalized electrons, the higher the melting point. So Na, K, Mg. Mg, remember? 2 electrons lost per atom, which means it's 2 plus ions, twice as many free electrons, better conductor of electricity, higher melting point. Apply a potential difference across the two and the electrons can move. Okay? Electrons, the atoms, sorry, can be moved around relative to each other. It's why metals can be hammered into shape. They are ductile. Okay? They can be drawn out into long, thin wires. And melting point for that is less than that, is less than that. Because 1, 2, 3, okay, numbers of electrons given off. As you go down the group, they get bigger, but you've got the same charge, so you have weaker attraction between the bigger charge, the bigger molecule, sorry, and the electrons. Therefore, as you go down a group, boiling point gets less, melting point gets less, and that is bonding. Okay, pause please. Okay. We're going to look briefly at shapes of molecules in terms of how their shape is determined by their electron configuration. And to begin with, we need to know what a covalent bond is. We know that. We know what lone pairs are. And we know, electrons are negative and they repel each other. So, if you have something like AlCl3, and it's got 3 bonds, and those bonds all contain electrons, and electrons repel each other, those bonds are going to want to move far away from each other as they possibly can. And in this case, they move until they are equally spaced around the aluminium atom. Okay? And this is called valence shell electron pair repulsion theory. If somebody wouldn't mind getting that door for me, please. Okay? So, muscle focus. What happens, okay, is they move to as far apart as they possibly can be. Okay? So that you've got minimum repulsion going on. And that's probably one of your key phrases. They've moved to a position of minimum repulsion. Okay? So, if you have 2 bond pairs, then they're going to get as far away from each other as possible. Okay, so that's going to be 180 degrees. It's going to be linear. If you have 3 bond pairs, it's trigonal planar. That's your Mercedes-Benz symbol. Okay? If you have 4, it's tetrahedral. Okay? 5, trigonal bipyramidal, 6, octahedral. We'll look at these structures in a bit more detail, but you are expected to know these names, these bond angles, and to be able to give an example. So, let's consider them one at a time. Beryllium chloride is covalently bonded, 2 pairs of electrons. They're as far away from each other as possible, 180 degrees. Aluminium trichloride, 3 bond pairs, as far away from each other as possible, 120 degrees. Trigonal planar. If you add another atom to that, then these guys are going to get repelled downwards a little bit. This is 109.5, and this is your tetrahedral structure. It's tetrahedral because if you have the full thing, the full space filled, okay, you've got a triangular-based pyramid, okay, in terms of solid faces. And where are they? There they are. So there's one face, you've got another face there, and another face at the back. Therefore, 4 sides in total, hence tetrahedral. And methane, and there it is, and there's your tetrahedral structure again. If you go to PF5, you end up with this one. It's called trigonal bipyramidal, and the reason it's called that is because it's trigonal pyramidal, i.e. tetrahedral. 1, 2, 3, 4. So there's your tetrahedron with your other tetrahedron underneath it. Okay? So trigonal, bi meaning 2, pyramidal. Between these two pairs there, that's 90 degrees. Between those there, it's 120. Which moves us on to SF6. 6 pairs of electrons, 90 degrees between each of them. Octahedral. Oct means 8. And that's because you've basically got, if you consider those as the base of a pyramid going up to there, you've got 4 sides, and then another 4 sides of the pyramid going down to there. There you have your octahedral. So, we have like bond pair repulsion, right? And then we have lone pair bond pair repulsion. And the lone pair is going to be closer to the atom, which means it's going to repel that away more. And we have 2 lone pairs, and they're going to be close to the atom, and they're going to repel each other more than those 2 repel each other, which is more than those 2 repel each other. Yes? So what happens is those distort the shapes. If we have ammonia, it's got 3 bond pairs, 1 lone pair. Now, it should be tetrahedral, and it is, except that that's a lone pair, so that repels more than those 2 do, which means it pushes them further away, which means it pushes them closer together, which means it's 107, and that shape is now called pyramidal. Ammonia, 107 degrees pyramidal. And there's some nice little shapes for you. Water has 2 lone pairs, and they repel each other more than the lone pair to the bond pair, and the bond pair to the bond pair, and what you get, whoops, lost it, 104.5 degrees. And this is bent or V-shaped or apparently angular. From here on in, there are a couple of weird little ones. Xenon tetrafluoride, where you've got 2 lone pairs, 4 bond pairs, and you end up with a square planar structure. Calculating the shapes of ions, and so on. I don't really feel that we need to go through it. What you do need to do is be able to spot something that's similar to something that you've previously studied. So NH4 has got 8 electrons, 4 bond pairs, therefore it's the same structure as methane. And so on, and so forth. Double bonds, carbon dioxide is linear. Other examples you're unlikely to need to know this. That's tetrahedral, this is T-shaped, okay? And that one is umbrella-shaped apparently, not come across that one before. I'm not going to go through the questions, and that is that. Pause please.